So this is the final section of today's lecture, and we're going to do a bit of energy storage, but before that, I want to talk about energy efficiency and trying to save energy. So as an example of this is, I'm going to use light bulbs. So there was a European directive to actually change all the 100-watt light bulbs in European countries and put in low energy light bulbs. And you'll see why that's been done in the next slide. But the simple question I'm going to ask is, if all the light bulbs we use in homes in the UK are 100 watts, how many nuclear power stations do you think are required to power all the light bulbs in the UK? So simple question. How many nuclear power stations to power all the light bulbs in the UK if they're 100-watt light bulbs? Any ideas?
10.
Okay, 10, thank you. Any higher, any lower? So, I mean, again, this is quite difficult when students first hear the question. What you have to do to be able to do this is at least have an estimate of, first, how many homes are in the UK with light bulbs, how many rooms are in those houses that have light bulbs, and also how long are the light bulbs on every day. Now, this is out of the UK census to get numbers that we can try and solve this problem. This is just a guesstimate because we don't know accurately how many hours each light bulb will be switched on every day. But there are 23.8 million homes in the UK, and they have an average of 5.33 rooms. Now, you can see here that there's some castles, there's some large hotels, but then there's also one-bedroom flats. But the average number of rooms is 5.33 that are likely to have at least one or multiple light bulbs. Let's just assume that each of the rooms has one light bulb that's on for 4 hours per day. That at least gives us a number that we can work out, if they're all 100-watt light bulbs, how many nuclear power stations do you need to power all those light bulbs in each of those rooms. So when you do that, you end up with, it's about 2.13 kilowatt hours per home per day. And that's 50,700,000 kilowatt hours per day. When you work that out, you basically need 2 nuclear power stations to power all the 100-watt light bulbs. So actually 10 as a first guess, without going through any of this, wasn't so far out when you're actually making guesses about some of these numbers. Now, what the European directive started doing 10 years ago was that everything had to move to low energy light bulbs. Now, actually, to start with, it was some of these fluorescent tubes. There's actually sustainable issues around fluorescent tubes. Things these days have moved to LEDs, we'll talk about in a minute. But as a simple example, if we look at reducing the power requirement of each bulb from 100 watts to 10 watts, how much does this go down? Well, of course, it's a straight factor of 10. So now, if we put the numbers in, this goes to 5,070,000 kilowatt hours per day. That's actually equivalent to the wind farm that's south of Glasgow. So suddenly, rather than 2 nuclear power stations to power all the light bulbs, you can actually use a wind farm to power the light bulbs for all the light bulbs in the UK. So this is a very simple example how improved efficiency can reduce the energy consumption. And in doing so, you can substantially reduce what you actually use to power the electricity. So in this case, I put in nuclear power stations. This could have been a coal-fired power station emitting a lot more CO2. Suddenly we've got renewables that can actually be used for many of these applications. So if we look at LEDs, well, actually, in terms of the number of lumens coming out, there are some 1-watt LEDs now with the same amount of light coming out as the old tungsten 100-watt light bulbs. So now again, this is another factor of 10 reduction in the energy consumption. And in fact, with this, you could easily use photovoltaics on the panels of the homes. That reduces your transportation as well and the infrastructure requirements. And this is one way you can substantially reduce the requirement for energy generation. And the bigger these power stations are, the more likely it's going to be gas, coal, or some fossil fuel that's used. So you can see that we've gone from these large power station requirements to something that you can actually, there are many photovoltaic solar farms that cover this total power generation over relatively small physical areas. So suddenly just moving to LEDs in a country, you can actually substantially reduce the amount of power stations that are required. Now, in fact, just to show the numbers that are actually quite important for this. So if we go back historically even longer, people use candles. When electricity came along, start of the 20th century, then light bulbs and the incandescent light bulb really started. Halogen bulbs came along a little bit later, 60s and 70s. These compact fluorescent, you can see that you're getting 5.5 times more light out than a tungsten light bulb. White LEDs, well, actually most of them now are over 150 lumens per watt. So 15 times brighter per watt of electricity than a tungsten light bulb. And certainly in Glasgow, and the UK, we use these orange street lamps. And that's simply because it's a sodium vapor lamp that are extremely efficient. So this is why in many parts of the world, street lamps are yellow, because simply it's a very efficient light bulb. So that's one example of reducing energy consumption. What are the other things? Well, so install low power lighting everywhere. We'll talk about when we look at thermal heating. We'll talk about insulating houses. In particular, the Germans have this passive house standard that actually reduces the space heating requirements in domestic properties by a factor of 7, at least from typical Victorian properties in the UK. Improved efficiency of space heating. We'll talk in the third lecture about combined heat and power. This is a concept that actually Glasgow University is using. So any waste from the rooms in Glasgow University is actually fed to local domestic properties to heat them. So combined heat and power is taking waste either from industry or in our case from education and sending the waste heat to domestic properties so they use less fuel to actually heat them. Improved efficiency of electrical products. Well, here there's quite a lot in the UK about national grid. If we look at the internet now consumes something like 5% of all the electricity consumed on the planet. That's been growing at an exponential rate. It's predominantly watching videos through the internet that causes a problem. That's the biggest growth area. So ICT is a big area that's growing. Domestic properties, improved electrical use there. There's a little bit you can do, but not very much. And as we saw earlier today, transport is an area that could actually have major reductions in energy use. Because if you use petrol or diesel, 75% of the energy from the fuel is losses that's thrown away predominantly as heat. So only 25% of the energy of the fuel in a vehicle is actually used for kinetic energy or for the entertainment or heating and cooling systems in the vehicle. Everything else is thrown away because in the diesel cycle, it's relatively inefficient. Now, a question here, in fact, I'm not going to answer this today, but something people might want to think about, are electric vehicles a practical method to reduce CO2 emissions? Now, certainly, a lot of people are saying yes, but it depends on how much CO2 comes from your electricity generation, whether this is true or it's not true. It also depends on the life cycle CO2 And you need to drive a lot of miles in an electric vehicle before you actually get the break even and the fuel becomes the dominant CO2 emission, because the life cycle CO2 dominates most vehicles. Right, to finish off today, we're going to do a little bit about energy storage. So somebody early on made the point how important energy storage actually is. And the key problem with renewables, and many of the renewables like wind, like solar, when we start to look at them, is that you don't get the energy all the time. So you have to store that energy before you consume it. But also more generally, it's seldom that you're generating the right amount of energy when the consumer needs to use it. So in most countries, during daytime, there's much larger energy consumption than during the night. So when people are sleeping, there's a lot less energy consumption. Storing energy later is not always easy. So small scale, we all have batteries, whether it's in our mobile phones or laptop computers, other portable ICT devices. I'll show you what the energy density of those batteries are. And this is another issue around electric vehicles that needs to be thought about. But when you get to large scale energy generation, storing what comes out of a gigawatt nuclear power station is extremely difficult. And for large scale storage, it's a real problem. And if anybody wants to make a fortune, that's an area that if you manage to solve that problem and patent it, you're likely to make yourself a fortune. So rechargeable batteries. Well, this is the basics of one type of lithium-ion battery that is probably what you've got on the laptop computer if you're using that to see these lectures. And what you typically have are two metal electrodes. They're made both with lithium. One's lithium cobalt, one's lithium carbon. And you have an electrolyte, typically an organic solvent, and you get reactions going on depending on which way you have these terminals as positive and negative. So this is basically whether you're applying a load and getting electrons flowing out of the battery, or whether you're putting electrons into the battery to recharge it. So at the positive electrode, you have this decomposition that you end up producing lithium ions into the electrolyte, and you also create in the same process a number of free electrons that basically get released when you're actually powering a load. At the negative electrode, you can recombine those when you turn the polarity around. So if you put electrons in, what you end up is recombining with the carbon, and you form lithium carbon on that electrode. Now, here's some of the key data around batteries. Remember, we spoke about petrol being something around 50 megajoules per kilogram. So if you look at the best lithium-ion battery, in research, they're now about 1 megajoule per kilogram. So they have 50 times less energy per kilogram than a battery. Sorry, a battery has 50 times less energy than petrol per kilogram. So this is one of the potential issues with electric vehicles and why there's a distance issue. You have to have 50 times the mass to actually be able to power an electric vehicle than if you use petrol. It's not quite like that because of the efficiency differences between electric motors and petrol engines, but it's a pretty high number. It's actually 25 when you do everything in. So you can see already that the energy density when you go to transport is a key property you have to look at. Now, it gets even worse when you look at aviation, because it's a lot more energy to get something into the air because of the potential energy. So this is partly what the Ben Nevis and the climbing the mountain example was about. In most areas, increasing potential energy costs you more energy than increasing kinetic energy. So going along the flat with transport consumes a lot less energy than going vertically in an aircraft. So let's just look at some other forms of storage as well. So capacitors and supercapacitors. So this is just taking two metal electrodes, having some sort of insulator between them, and you can load these up to have electrons all in one side, a deficit of electrons in the other when you charge them, and then you discharge through a load. Now, capacitors can actually be charged and discharged much faster than batteries. So one of the big disadvantages of lithium-ion batteries is you have to charge them relatively slowly, otherwise they explode. So the other thing with batteries is you have to be concerned if the energy density gets too high, because you basically have an explosive. And this is something, when people talk about improving the efficiency of batteries, is frequently forgotten. That actually energy density is high in a lot of explosives.
But the capacitors and the supercapacitors also have certain limitation, like they discharge quite fast as compared to the batteries. So we can't store the energy in the capacitors or the supercapacitor for a long period of time.
That's correct. I'll talk about that in a minute. So the energy you can store in a capacitor, it basically goes as a half the capacitance times the voltage squared you've got across the two metal plates. The capacitance is the free space permittivity, so that's 8.85 times 10 to the minus 12 farads per meter. The relative permittivity of this dielectric, so the higher you make this relative permittivity, the more energy you can store. The area of the metal plates, and it's inversely proportional to the distance. So the larger you make this distance, sorry, the smaller you make this distance, the more energy you can store. So the other way of thinking this is it's also the square of the charge that you have in each of the capacitor plates divided by the capacitance. So the major issue for these capacitors, even the supercapacitors, it's an even lower energy density that you've got compared to batteries. So remember, batteries were getting towards 1 megajoule per kilogram. This is 2% of that. And leakage currents. So as the student said, leakage currents are a big problem. That charge leaks both through the dielectric, but also out and away from the metal plates. And that gives you a finite amount of time that you can actually store the charge on the capacitors. And it's a big issue for long-term storage. So again, supercapacitors are relatively good for something that's quite small. There are a couple of areas where you can store power station levels of energy. And one is hydro. And in Scotland, we've got a couple of examples of this with what are known as pumped storage schemes. Now, again, we'll go into hydro in great detail in later lectures. And as I said earlier, hydro doesn't work everywhere, because in this case, you have particular mountains, a dam was put across, and actually the generating turbines are 360 meters beneath the Cruachan Reservoir. So this is up a mountain. It's only 50 miles away from Glasgow. If anybody does get to Glasgow and wants to go and visit it, it's a lovely day trip near Loch Awe. There's a reservoir at the bottom, 360 meters, and it can't run for very long if it wants to run at its maximum power of 440 megawatts. Now, in terms of the power it can generate, the power is its efficiency. We saw earlier most of these hydro schemes are about 90% or so. The density of the water, the gravitational acceleration, so 9.81, the height, or what's known as the head of water. So for Cruachan, that's 360 meters. And then Q is the volume flow rate. So how quickly this volume of water drops the 360 meters determines the power that can be emitted. And in this case, that gives the 440 megawatts maximum power. Now, there's a few other areas you can use that are less well used. One that's being looked at for transport, and there's been a number of automotive companies have trialed these things in the UK, are flywheels in vehicles. So the flywheel, you basically store up energy when you brake the vehicle, you basically transfer from the braking, the inertia, and put that into the storage wheel. The energy you get from this inertial flywheel is 1/2 times the moment of inertia times the angular frequency omega squared. And the moment of inertia I is a constant k times the mass that you've got rotating times the radius squared. And this constant k really is determined by how the mass is distributed on the flywheel. So if you've got a uniform disk, k is 1/2. If you manage to have a thin mass just around the outside of this with spokes, then you end up with k close to 1 for the thin ring. So if this is more like a bicycle wheel with a mass distribution, then k is close to 1. So overall, you end up with the energy being 1/2 times this constant k, times the mass, times the radius squared, times the angular frequency squared. So since the angular frequency is squared, it's much easier to rotate faster than increase the mass to get to higher energy stored. But these things really can be quite dangerous because where they've been trialed, some of these omegas can be kilohertz. And for very small scale, they can be hundreds of kilohertz. So the energy stored can really be quite big. The other thing with flywheels, they can be energized and de-energized much more quickly than batteries. So again, batteries have these problems of the time it takes to charge them. And also the same thing if you need to get the energy very quickly. Now, for vehicles, normally that's not the case. If you want to have an aircraft taking off, that's much more of an issue, and it's much harder to use batteries for aircraft. So this final one we're going to look at is actually a much more practical one that we'll talk about when we get to thermal solar, and it's used in many parts of the world. What you basically do is you store the energy as thermal energy, and this is partly because a lot of uses, particularly of heating and cooling, it's thermal energy you actually want to deal with and not electricity. So we had earlier that the energy, or the thermal energy, is the mass times the specific heat capacity times the change in temperature. You just take a mass, it can be a mass of water, it can be a phase change material, and water is actually pretty good because the specific heat capacity of water is actually very high compared to many other materials. It's also got an energy density that actually is not too bad. So it's 0.418 megajoules per kilogram. So it's about half the energy density of a lithium-ion battery. Phase change materials are also being looked at, but many of those are not, tend to have lower energy densities than water. And also, this is how ground source heat pump systems can work as well. That it can sometimes be storing in a thermal mass that you release to the property if you want to heat or cool. You can use the same approach for cooling by pumping the heat in the opposite direction. So this is why heating and cooling are so closely related. Now, actually, the final one I've put in here are fuel cells. Now, fuel cells, as you'll see in a minute, they are being researched at the moment. There are a couple of commercial examples, but there's still a whole series of issues with fuel cells of actually using them in large scale for transportation in particular. What's very good about fuel cells is that you put hydrogen in as a fuel and you put oxygen or air in. What you end up getting is that the hydrogen in the electrolyte process at the anode is converted into atomic hydrogen. So the molecule with a bond, the bond is broken, and in breaking those bonds, you release 2 electrons, and they basically give you the current that you power whatever your load is going to be. What makes the fuel cell so attractive is that the waste that you get out of it is water. So it's not carbon dioxide, it's got nothing to do with carbon whatsoever. You're releasing just water vapor into the atmosphere, And actually releasing water vapor into the atmosphere has a negative effect on climate change and global warming. It actually improves from greenhouse gases, not substantially, but at least a little bit. Now, when you look at how much energy you can get out of this, it's actually pretty high. What's key though, is if we look at energy density of hydrogen, actually it's a colossal figure. So this 143 megajoules per kilogram, so that's 143 times higher energy density than lithium-ion batteries, or it's 3 times higher than petrol. But the real problem is that's density, and hydrogen is a very low density gas. So when we look at the density per unit volume, so this is megajoules per liter, actually it's a pretty low number compared to many of the fossil fuels that are used at present. So, the other key problem with hydrogen fuel cells is, how do you generate hydrogen? It's a very expensive process to do. Typically you need catalysts, and normally it's done actually getting the hydrogen from methane gas, which in the process ends up releasing carbon dioxide into the atmosphere if you don't capture it. So we'll talk a bit about some of the ways of generating hydrogen later in the course. So one of the problems with politicians, and the CEO of Peugeot has pointed this out, is that for transport, they can easily think about what comes out an exhaust pipe. But actually, when it comes to decarbonizing transport, life cycle and what goes in when it's electricity is a much bigger issue for reducing CO2 emissions from transportation. Right, that's all the energy storage for today. A final slide, and this is the other really important slide from today's lecture. And this will get over part of the reason why renewables are not substantially used, certainly in the UK and not in other parts of the world. Energy density is important, and we'll come back to this when we look at different generating mechanisms, because when you start to look at fusion at the top, and there's hydrogen fusion, there's the complete transfer of mass into energy using Einstein's famous formula. When we start to look at fission, you get these enormous energy densities from uranium and plutonium being used as nuclear fuel. And we'll talk about that in lecture 3. Hydrogen, as you've seen, has got an enormous density, but the volume's pretty high. And petrol and even trees, well, you can see, in fact, wood and TNT are quite close. Lithium-ion batteries are starting to get close to TNT, high explosive, in terms of energy density. And then when we get down to hydro and wind turbines, you can see that the energy densities are very low. And this is really the problem with renewables. You need a lot of wind turbines and a lot of photovoltaics and a lot of water and hydro schemes to get the equivalent of what you get with coal, oil, gas, or nuclear. And we'll talk much more about this as we go through the individual generation mechanisms. But for today, that's everything I want to speak about. So what we've gone through is defining energy, renewables, sustainable energy, net zero, and power. We've spoken a lot about energy generation and some of the uses and defining those. We've looked at carbon dioxide emissions and shown you how you can actually calculate that, at least for the fossil fuels at the moment. Electricity generation, a little bit about distribution, which we'll talk much more when we go through particularly thermal power stations. And we've spoken at the end about energy storage, showing some of the issues around that and how much energy density different techniques can actually do. And for a bit of entertainment at the end of what's been a long week, I imagine, for many people, here's a bit of fun.